Hello, welcome once again to our YouTube channel. Thanks for subscribing to our channel. We really appreciate you. It's nice coming along with us. Today we want to look at a particular important topic, a topic that is very crucial to our understanding what chemistry is as it is today, and that is talking about the periodic table. In this particular tutorial, we will be getting to understand a couple of things. We will be learning how to form or to construct a standard periodic table, objectives, learn how to construct a standard periodic table from scratch. Yes, and number two, to know how to write the electronic configuration of elements. Electronic configuration of elements, a very crucial step into how to place elements into the periodic table. And thirdly, to learn how to place or locate any element on its specific location on the periodic table. This and more are some of the things that we will be coming to learn today as we take this particular tutorial. So I encourage you to try as much as possible to come along with us as we will be talking or saying a whole lot about the things that we have today. The periodic table is the major classification that is found in chemistry. It is the most important system of classification in the study of chemistry. It is actually constructed by a Russian scientist called Mendeleev. It was constructed by a Russian called Mendeleev. Far back in the year 1869. Yes, we need to take note of that. It was created by this particular scientist called Mendeleev, and that was in the year 1869. So this particular table has been of great help in understanding what chemistry is about. Mendeleev used the property of each of these elements, majorly the atomic number of the elements, in arranging the elements into the periodic table. Mendeleev used the major property of these elements, which happens to be the atomic number, of the elements. And what made this very possible was because each of the elements have distinct atomic number. No two elements have the same atomic number, and that was why it was easy for Mendeleev to make use of this property in explaining or designing what the periodic table is, as it were. So that's just a few things that we need to understand about the periodic table. Now the periodic table is created to have rows and columns, something that we will come to understand very shortly. Now before we move further, let me quickly talk about what we know as the modern periodic law. We have what is called the periodic law. Let me put that here. The modern periodic law, that is simply what I just talked about, having it as the function of the atomic number. The periodic law states that the property of every element in the periodic table is a function of the atomic number. This law states that the property of every element in the periodic table is a function of their atomic number. So it was with the help of the atomic number that all of these elements were being placed into their very position in the periodic table. So having said this, now let us now go to look at the components of the periodic table. Components of the periodic table. Now when we talk about the components, we are made to understand that the periodic table is majorly constructed using rows and columns. So we have the vertical part of the periodic table, or the verticals in the periodic table, to be what we refer to as the groups. These are the vertical columns that are found in the periodic table. The group is divided into 8 major groups. There are 8 major groups. With some constructed between some other groups. We'll get to understand that shortly. And then, so like I said, we have them ranging from group 1, 2, 3, 4, 5, 6, 7, 8. We have them like that. And then the period, we have them to be horizontal. These are the horizontal lines drawn from left to right, which is currently having up to 8 periods. We can have that up to 8 periods. Now, if you have discussed this, let us quickly look at what we are talking about. Let me use this to help us understand what the groups are like. So we have the groups constructed like this. You can see them in just rows drawn from top to bottom, while in the case of the periods, we have them drawn across like this. So shortly, I will help us understand what this thing that we're talking about now, what they actually mean. So let us quickly look at the classification like we have talked about, how the groups are. So parts of the periodic table now. Looking at the major parts of the periodic table, we have the S block 1. We have 2. Three. We have the D block. These D block elements, they are usually found the D block elements, which are referred to as the transition elements, are found to exist between the group 2 and group 3, starting on the 4th period. So that is where you find the D block elements. They are found between the group 2 and group 3 of the periodic table on the 4th period. And then we move over to the F block elements. These are called the inner transition elements. They are called inner transition elements. This set of elements are divided into 3 series. Divided into 3 series. The first one we have is the lanternide series. And the third one we have there is the superactinide. Superactinide series. So these are the sets of series that we have in the F block element. This set of elements are found between group 2 and the first set of elements on the transition element, which is the D block element. Between group 2 and 3, between group 2 and 3, right before the D block elements. But starting on period 6. So these are the parts of the periodic table that we have. So briefly, let us look at a sketch of what the periodic table will look like. Like we said, we have the S block. So I will just put them in perspective. We have the S block that is found somewhere in front like this. We have the S block that is found then far to the right is where we now have the P block elements. We have the P block elements. We have them drawn like this, like that, and then that is, so this place here, like I said, this place is going to be our S block, and this place is our P block, and then we have the inner ones, which are the let's assume that this one is 1 2 3 4 5 6 7. So this is going to be our group 1, group 2, and from this back I have group 8. I have group 8, group 7, group 6, group 5, group 4, group 3, like that. So if I have that now, let's assume I have this here. So from here now, I'll be having from period 3, from what we just read about. From here now, I said that the D block element between group 2 and group 3, and it starts from the 4th period. So that is what we'll be seeing here now. So from the 4th period, far to the right beside the P is where we now be having the D block elements. So we have it like this, something that looks like this. We have it here, like this. So let's say that this is our D block elements now. All of the elements that are found in this region here, we said they are our D block elements. This one here, all of the ones that we have here, the ones that are here like this, we have them to be our P block. These ones here, they are the S block, and here we have the D block elements starting from the period 4. And then from period 6 is where we now have the last set of elements, which is what the ones we refer to as the inner transition elements. Let's say we have them around this place here. So something similar to this is what our periodic table will be looking like. Everything we'll be having from this place like this will be falling to our F block. Now the F block is usually taken out downwards. You usually see them taken out, they are brought down. All of these parts here, they are usually brought down to make room for the periodic table so as not to make it confusing. But for the sake of this particular lesson, for you to be able to understand where each of these elements fit into, this is how the periodic table will look like. And by the time you are done creating the framework of the periodic table, something similar to this is what you will be having. By the time you are done creating that part of the periodic table, this is what you will be having after you have constructed everything like you have been told to do. So this is what the periodic table framework looks like. So you can see right here now that we have the S block, we have group 1, group 2 in our S block, and then here we have our P block from group 3, 4, 5, 6, 7, 8. This is our P block. So we have the D block as well here, which is the transition element, and then we have the F block here, which is the inner transition element. So if you look at it now, the D block element starts on period 4, while the F block element starts on period 6. And the transition element, both the D block and the F block, they are between the group 2 and group 3. So that is what we have talked about in the sketch of the periodic table. So now we have a framework, a solid framework for our periodic table. Now that we have this, then we need to go to understanding how to place the elements into their specific positions. Now it is key that you get to understand that, like we said earlier on, all of the elements are placed in specific positions of the periodic table based on their atomic number. So the atomic number is the major principle that we make use of in determining where each of these elements are being placed. So having said that, now we'll quickly look at the rules that govern the filling of elements into the periodic table. Now there are basic principles that we'll be looking at, but I will be specific about a particular one. We look at Pauli's exclusion, Hind's rule, but the one I'll be specific about is the Alva's principle. We have Pauli's, so we have his exclusion. We have the Hind's rule. But the one I'll be specific about now is the Aufbau's principle. That is the one I want to make mention of right now. And what is the Aufbau's principle saying? Aufbau's principle said in the building up of atoms, electrons enter into orbitals in order of increasing energy. States that electrons enter into orbitals of increasing energy. So how are we to know the order in which the energy is increased? And that is what brings about this particular system of arrangement as formed by the Aufbaus. So we have, remember, we are making use of the SPDF. So we have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, 7s like that, 7d, 7f, 8s, 8p, 8d, 8f, and so on. So this is now where the arrangement is made known. We have this. They are arrowheads. So what it means is when the arrow moves to this place here, it comes this way and start from here again. So the arrow moves down and then it comes this way to start from here again. And then when it gets to this place here, it comes like this to start here. So what I'm saying is when the arrow moves down from here to this place here. When it gets to the tip here, it comes to start from here again. It moves down to this tip here, goes to the next arrow, start from here, moves down. So with that now, what we will be having is going to look like this. Let's start from here. We have the first one here, which is 1s, comma, and after that we can see after 1s the arrow has gotten to the end here, then it moves to the next arrow, which is 2s. So we have that written as well, 2s, comma. After the arrow now, we can see that after the second arrow we move to the third arrow, and on the third arrow the first thing we can have there is 2p before 3s, because the arrow is moving downwards like this. So we have 2p followed by 3s. We have 2p, 3s, and after that we have on the next arrow, which is this one here, we have 3p, 4s. We have 3p, 4s, and then on that, after that arrow, this is the next line, this is the next arrow here. This was what we just finished talking about, 3p, 4s, followed by this one, which is 3d, 4p, 5s. So we have 3d, 4p, 5s, and then after that now, this is the next arrow here. This one here is the next arrow, this particular one here. So we have 4d, 5p, 6s on that particular arrow. 4d, 5p, 6s, and then on the next arrow we have 4f, 5d, 6p, 7s, followed by 5f, 6d, 7p, 8s, followed by 6f, 7d, 8p, and then if down here, if we add another line where we have 9s, so what we'll be having after 8p is going to be the 9s. Let me just put this, etc. Now, having understood this is the system of identifying all of these things. So we now need to understand that all of these elements now, they have their capacity. When we look at the s, it can carry less than or equal to 2 electrons. S can carry less than or equal to 2 electrons. And then the next one, which is p, can carry less than or equal to 6 electrons. The next one, which is d, it can carry less than or equal to 10 electrons, while the last one, which is f, can carry less than or equal to 14 electrons. We need this as a baseline, talking about what we'll be looking at now. So everywhere we have s, we know that s can carry less than or equal to 2. So depending on the atomic number of the element, we will be using that to identify or to place the number of electrons that we want to place on each of the electron configuration of this element. So let us look at a couple of elements, and then we'll write out the electronic configuration, so we'll be able to place them on positions on the periodic table. So remember we have this, so let us quickly pick a couple of elements. We write out the electronic configuration and then we'll move further from there. So let's start with, let's say we want to write the electronic configuration of neon. Neon has atomic number of 10. We listed as all of these here to be the electronic configuration as it is arranged by Aufbau. So the electronic configuration of neon is going to look like this. Remember, we are going to 10. So we start with the first one, which is 1s. So we are going to 10. So I said s can carry maximum of 2 electrons. So I have 2 electrons. So 10 minus 2 equals 8. So that means we have 8 electrons left. So I move to the next energy level, which is the 2s. 2s. Since I have 8 elements left, I can also take out 2, giving 2 electrons to this particular 2s orbital. So 8 minus 2 again will give me 6. So I have 6 electrons left. I can move to the next energy level, which is 2p. 2p can carry maximum of 6 electrons. We can see that here. I said that 2p can carry maximum of 6 electrons. So that is what we'll be looking at now. So 2p has, right now, neon, we have used 2 electrons for the first orbital, we have used 2 electrons for the second orbital, we are left with 6 electrons. And since p can carry 6 electrons, that means we are going to give that 6 electrons to p. So this is going to be it. So we have the electronic configuration of neon to be 1s2, 2s2 and 2p6. 1s2, 2s2 and 2p6. So that is what the electronic configuration of this particular element is. And then let's pick another one. Let's say we want to write that of calcium. Calcium, which has 20. So the electronic configuration is going to be 1s2, 2s2, that is 2 plus 2, 4. So 4 out of 20, we still have 16. We move to the next energy level, which is 2p. 2p, we can give this one 6 since we still have 14. So 2 plus 2, 4. 4 plus 6, 10. So out of 20, we still have 10. So we move to the next energy level, which is 3s. So 3s, s carries maximum of 2 electrons, so we give it its own 2 electrons. So out of the 20, we have used 12. We are left with 8, so we move to the next energy level, which is 3p. So 3p, if we have 8 electrons left and p can carry maximum of 6, so we can easily give it 6. That tells us we have 2 electrons left. Let us see. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6 again, that gives us 18. So we have 18 electrons used and we are going to 20. So 20 minus 18 gives us 2. So we are going to the next energy level after 3p. 3p is here, so the next energy level is 4s. So I write 4s. Since it is s, it can carry maximum of 2 electrons, and that is just the number of electrons that is left to complete the electronic configuration of calcium. So this is how electronic configurations are written. So having this as a foundation, we can now go into writing the configuration of different elements and placing them on the periodic table. So let me just use these two that we have written as a case study. If we have this to be the configuration of neon, if we have 1s2, 2s2, 2p6 to be the configuration of neon, now this is the highest s orbital, this one here, 2s2 is the highest s orbital. So this is what signifies our period. 2s2 here signifies our period. So the highest s orbital is 2. So that is going to be our position of neon, and then the group to which it belongs is going to be a p block element on the sixth period, the sixth group in the p block. The sixth group in the p block. Again, the period of neon is determined by the highest s block element. So the highest s block element, look at this one here now. For neon, we have 1s and 2s. So the highest s block is 2s. So that is what determines the period to which neon belongs. And then talking about the group where it will fall under, we said that the group is determined by the last electronic configuration here, which is 2p6. 2p6. So the group of neon is going to be under the p block, the sixth group under the p block. So if you remember, in our p block we have 6 groups. Let me quickly take us to that particular page. So this is it. In our p block we have 1, 2, 3, 4, 5, 6. So this is our 6 p blocks. So if our neon is from what we discussed, S2, it has 2s as the highest period. The highest s orbital is 2, so it belongs to period 2. So this is where we have period 2, and then any of these ones here, 1 2 3 4 5 6 7 8, will be where the neon falls under. But which of these 8 spots will we be having our neon? And that is where the period comes in. So the last thing we had there was 2p6. So p6, this is our p block, and in our p block we now have this one here to be number 6. 1 2 3 4 5 6. So this position here exactly is where we'll be having our neon. So neon will be written here. That is where the position of neon will be. Going to the next one that we did, calcium. Now the highest s orbital for calcium is 4s. 4s is the highest s orbital. Look at it now. We have 1s, we have 1s, we have 2s, we have 3s, and we have 4s. Those are the s orbitals that we have, but the highest of them all is this one here, the 4s. 4s is the highest orbital. Now that tells us that this calcium will belong to period 4. Calcium belongs to period 4. And then the group, now the group is determined also by this last this last orbital. So it is an s block element, and the s block position is s2. So in our s block we have 2 classifications. This is our s block. We have 2 classifications. So one, you can see it here, s1, s2. So it is with this now that we will place our calcium here. We said calcium belongs to period 4 and s2. So this is period 4, 1 2 here. And for s, we have it to fall under this one here. So this is where our calcium will be, Ca, calcium. So that is how we place elements in the periodic table. So let us quickly take a couple of elements at random. Writing the electronic configuration, we place them in their position on the periodic table. Aluminum has the symbol of Al. Its atomic number is 13. So this is how its electronic configuration will go: 1s2, 2s2, 2p6. We have 2 plus 2, 4. 2 plus 2, 4. 4 plus 6, 10. So we are going to 13. So we are left with 3 electrons. And after 2p, we have 3s. So we have 3s2, since s can carry maximum of 2 electrons. And then that means we still have one more electron, which is going to 3p. So p can carry maximum of 6 electrons, as we can see here, but we have just 1 electron left, so we put it here. So like we have said, we have our highest s orbital to be 3s. This one here is our highest s orbital. We have 1s, we have 2s, but the highest s orbital is 3s. So that is what signifies our period. So the period to which this element belongs to is period 3. Period 3. And then for the group now, we have it to come from this one here, the last orbital. The last orbital is 3p1. 3p1. So the p block is where we have this particular element, aluminum, and we are in the p block, the first port in the p block. So we have it to be in the p1. So we have period 3, and then our group is p1, where we have that particular element. Period 3, this is period 3 here. This particular row here is period 3, or column rather, the row. This place here is period 3, and then we are coming to the p block. This is the p block element, and then in the p block element we have it to be the first port. The first port. So I'm putting that here. Period 3 in the first port, aluminium. Aluminium. Okay, let me try to put a demarcating line to help us navigate easily. All right, so we have that. So let's take another element. Since we have successfully placed aluminium in its own position, let's take vanadium. Vanadium, it has atomic number of 23. So its electronic configuration is going to look like this: 1s2, 2s2, 2p6, 3s2, following what we have up here, then 3p6. Okay, this is 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18, and we're going to 23. So we have 4s2, and then 3d, this is 23d3, so this makes 23. 2 plus 2, 4 plus 6, 10 plus 2, 12 plus 6, 18 plus 2, 20 plus 3, 23. So now that we have that, this here is going to be the highest S block. This one here, 4s, is the highest S block. We have 1s, 2s, 3s, but the highest S block is the 4s orbital. So that tells us that this particular element belongs to period 4. And then for the group now, we have it coming from this particular last orbital here, the D block. The D block, which is what? The third port. The third port in the D block element. So D3, that is where we are going to now. So period 4 and then group D3. This is where we have it. This is our D block element here. This is the D block element. So period 4, this is period 4, everything here, but we are going to D. So we said D3. So period 4, and this place here is our D, and then position 3, D3 in period 4. So this way is where we have our element. That's where we have our vanadium here. That's where we have vanadium. So let's take another element. Selenium has 34 as its own electronic configuration. So that will give us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, that is 30 I think, 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12 plus 6, 18, plus 2, 20, plus 10, 30. So we have 30 already, and we are going to 34. After 3d, what we have is 4p. So let's write our 4p, and 4p can carry maximum of 6 electrons, but what we have left is 4, so we just put the 4 here. So that is where we are going to. This is the electronic configuration of selenium. And for this one now, we have the highest S block to be 4s also. 4s is the highest S electron, the highest S orbital. So that marks our period. The period is going to be period 4. And then for the group, this is where the group comes from. Our last orbital, which is the 4p. So we are going to make use of the p block element, then number 4, the fourth port in the p block element. So p4. So we are going to period 4, and then under the group we look for the p block and then the fourth port. That's where we are going to now. So 4p4. So this is the fourth period. This one here is the fourth period, and then we are going to the p block. This is the p block here, and the fourth port, 1, 2, 3, 4. This port here is where we have selenium. That's where we have selenium. So that is what we want to write here. Selenium. That is where we have selenium. So let's take another element. Let's take some random elements. Let's take platinum, for example. Wow, this one has a very long electronic configuration. Platinum, it has its own atomic number is 78. 78. Okay, let's see. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4D10, 5P6, 6S2, after 6S. Okay, let's count what we have got into here already. 2 plus 2, 4. 4 plus 6, 10. Plus 2, 12. Plus 6, 18. Plus 2, 20. Plus 10, 30. Plus 6, 36. Plus 2, 38. Plus 10, 48. Plus 6, 54. Plus 2, 56. So we have 56 already. The next, I'm going to 78. So the next one we have after 6S is 4F. 4F can take 14. 4F can take 14. We already had 56. 56 plus 14 will now give us 70. And then we move to the next one after 4F, which is 5D. 5D8. Yes, 5D8. So look at this now. Let's quickly count again. 2 plus 2, 4 plus 6, 8, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, plus 14, 70, and then plus 8, 78. So this is going to be the electronic configuration of platinum. And since we have written this now, we can actually place it in its own position on the periodic table. So the highest s orbital here is 6s. 6s is the highest s orbital, so that marks its period on the periodic table. So it belongs to period 6. And then the highest orbital there, we have the D8, D block 8. So we are going to, in period 6, we go to the D block and then port 8. That is where we are going to. That is how we get its group, D8. So period 6 and then D block 8. That's for platinum. Period 6, this is period 6. Everything here is period 6. But we are coming to the D block and then 8. So this is period 6. So this position here, period 6 and then D block 8. So this is where we have our platinum. That's where we have our platinum here. D block. That's how we get elements written into the periodic table. Let's take more elements, try to fill as many as we can. Okay, let's take antimony for example. Antimony, we just keep taking random elements. Antimony has its own symbol to be SB, and it has the electronic configuration of 51. Let's check its own configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5. Okay, let's count first. At this point here, 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36. Okay, this one is, we have gotten to 36 now. 5s2 plus 4d10, 36 plus 2, 38 plus 10, 48. Okay, the next one there is 5p. So 48, we are going to 51. So this one is going to be 5p3. 5p3. So 48 plus 3 will give us 51. So this is the electronic configuration of antimony, 51. This is the electronic configuration. So this one here happens to be our highest s block, 5s. 5s is our highest s block, so it belongs to period 5. It belongs to period 5. And then this is our highest orbital, p3, so that signifies the group p3. So it means in the p block we have the third port to have antimony in it. So period 5 p3, this is period 5, this is period 5, and then p block, the third port. So this is where we have our antimony. That is where we have antimony, this place here, period 5 port 3, antimony SB. That is where we have our antimony. Let's take one that will give us F block. Let's take an F block element. Okay, let's take promethium, for example. Promethium has 61. Promethium has 61 as its own atomic number. 61 as its own atomic number. So let's write its configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, after 5p, 6s2. Let's count this one first. We are going to 61. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, and we are going to 61. So we have 5 left. After 6s we have 4f. Okay, 4f, and we have 5 left. So this 66 plus 5 will give us 51. So that is where we are going to 4f promethium. Okay, so let's look at its position now on the periodic table. The highest s block there is the 6s. The highest s block is the 6s, so that tells us that this particular element belongs to period 6. That is where this element belongs to, period 6. And then for the group now, it comes from this one here. It is an F block element in the port 5. F block port 5. So first of all go to period 6, and then in period 6 we look for the F block port 5. This is the period 6 here, period 6, and then we are looking for the F block. This is the F block and port 5. So period 6 port 5, this place here. That's where we have our promethium, this place here, promethium. That is where we have our promethium. And then let's take another one. Let's take mendelevium. Mendelevium has MD as its symbol, and it has 101 as its own electronic configuration. 101. So let's write 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, P6. The reason why I'm writing it like this is because I know where I'm going to 101 for the atomic number of Mendelevium, so it's very long. So I will just be putting the highest number of the orbital for now until I'm close to about the 100. Then I start counting. So 6p6, 6p6, 7s2. Okay, let's count first. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, plus 10, plus 14, 70, plus 10, 80, plus 6, 86, plus 2, 88. Okay, to S2 I have 88. After S2 I have 5F. Already I have 88. So the next one here now after 7S is 5F. 5F can take 14. But do I have up to 14 left? 101 minus 88 will give me 13. So since my F can carry maximum of 14, I will just put my 13 here. So 5F13. Wow, that is the electronic configuration of Mendelevium. So looking at that now, considering everything that we have said in the past, the period is going to come from the highest S block. So the highest S block is 7S. You can see it here. 7S is the highest S block here. We have other S block like this is 6S, 5S, 4S, 3S, 2S, 1S. But the highest S block is the 7S. So that tells us that this particular element belongs to period 7. And then the highest orbital is the 5F. 5F. So that is where we'll be going to now. The F block and port 13. In the F block, we look for port 13. So that is how we get the location of this particular element called Mendelevium. F13. F13. So this is period 7. This is period 7. And then this is F block. This is F block. So we are going to 13. This is where we have it here. This particular place here is where we have our Mendelevium. MD, Mendelevium. So it's just as simple as this. This system that we have used now to identify these electrons or these elements in this particular periodic table is the same method that you use in putting all the elements into their position on the periodic table. Let's take one or two more examples before we wrap it up. Let's take Neptunium. Neptunium has atomic number of 93. So let's write its own configuration. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, let's see, 6s2, 7f10, 7f14, 5d10. Let's count what we have gotten to for now. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, plus 14, 70, plus 10, 80. Okay, we have gotten to 80 right now. And then after D, 5D, we have 6P. So that's 86, 88. 88 out of 93 will give us 5. 88 out of 93 will give us 5, so we'll put that here. So this is going to be the configuration of this particular element. We have 7s as our highest s orbital. 7s is our highest s orbital, and we have 5f. So the f block, okay, let me take it one after the other. 7s is our highest orbital, so that signifies our period 7. And then for the group, it belongs to the f block element and the 5th port. F block and the 5th port. That is where we have the Neptunium, period 7 and F5. Neptunium is in period 7. Period 7, this is period 7. Period 7 and the F block 5th. This is here, this place here is where we have our Neptunium, directly under our Promethium. Okay, let's take radon. We're taking radon, for example. Radon has atomic number of 86. 86. So let's write 1s2, 2s2, 2p6, 3s2, 4p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10. So this is up to this place is 80. Then 6p6. Since we are going to 86, 6p6. Yes, so this is the electronic configuration for radon. So like we have said, this is the highest s orbital, 6s. 6s, you see we do not have any s after this 6s, so that's the highest s orbital. So that signifies our period. The period is period 6, and then this one here signifies the specific position on period 6 where we will have radon, which is what, the p block and the 6th port on the p block. So we have it to be the p6. This is our period 6. This is period 6 down here. All of these things here like this. Where we have promethium, we also have platinum. That is our period 6. So on that period 6 now we are going to the p block. On that period 6 now we are going to the p block, and this is where we have the p block. So 1, 2, 3, 4, 5, 6. This is where we have the 6th one, and that is where we have the location of radon. That is where we have our radon being written here. Radon. Lanthanum is a lanthanide element, like the name implies. Lanthanum. Lanthanum. It has atomic number 57. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. Okay, this is 10, 20, 30, 38, 4d10 as 48, 5p6, 48, 54, 6s2, then 4f1. Lanthanum, let's count again. We're going to 57. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, plus 1, 57. All right. So since this is our configuration, this is our S, the highest S block, which is 6. So that tells us that this particular element belongs to period 6. Period 6. And then the group now, we have it coming from our F block, which is the first port in our F block. The first port in our F block in period 6. So that is where we are going to now. F1. Period 6, F block 1. This one here. This is our period 6. This line here is our period 6, and we have this one to be our F block. This is our F block here, and this is the first port in our F block. So that is where we have our lanthanum. Let's take rutherfordium. Rutherfordium has atomic number of 104. 104. Okay, let's see. We have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14. Okay, let's count. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36, plus 2, 38, plus 10, 48, plus 6, 54, plus 2, 56, plus 10, 70, plus 10, plus 14, 70, plus 10, 80, plus 6, 86, plus 2, 88, plus 10, plus 14, 88 plus 14 will give us 102, and then we are going to 104. So that means we have 2 more electrons. After 5f, we have 6d, 6d2. Alright, so this is where we are going to. This is 102 electronic configuration for rutherfordium. So like we have done in the past, this is our highest S block, so that gives us our period, which is period 7, and the group is going to come from this last energy level, which is D block 2, D block and 2. So period 7, and then D block, second port in the D block. Period 7, second block in the D block. This is period 7. This period 7. This one here, and then we're coming to the D block, second port. So this one here is where we have the second port in the D block. That is where we have our rutherfordium, RF rutherfordium. So this is how we just randomly work on the elements in the periodic table, and we keep putting them into their positions. Let's take another one that is, okay, let's take francium, for example. I want to take francium now. Francium, it has atomic number of 87. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, that's 80, 6p6, 86, and then 7s1. Let's count. 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20, plus 10, 30, plus 6, 36 plus 2, 38 plus 10, 48 plus 6, 54 plus 2, 56 plus 14, 70 plus 10, 80 plus 6, 86 plus 1, 87. So this is the electronic configuration of francium, and since this is our highest s orbital, 7s is our highest s orbital, that is what represents our period. So our period is 7, period 7, and coincidentally that is our last energy level also. So since it's our last energy level, s block is going to be our where the elements fall to in the group, s block and first port, so s1. So period 7 and then group in s port 1. So this is period 7, this one here, and we have our s block to be this one here. This is our s block, and this is first s block. So this place here is where we have our francium, this place here, francium. So this is just how we keep identifying the location of elements on the periodic table. I hope with this particular video that you are able to understand how elements are being placed on the periodic table using their electronic configuration that is gotten from the respective atomic number of each of these elements. Just follow us on our channel for new interesting videos that will help shed light on so many hidden facts about chemistry as it is. Thank you very much for coming along with us. If you are yet to subscribe to our channel, don't fail to do so, as subscribing to our channel has a whole lot of benefits to offer you. If you have subscribed, don't forget to put on the notification button so you get easily notified of subsequent uploads when we put them up on our channel. Like our content, share them with your friends, let them also benefit from what you are getting. And please, if you have any question whatsoever, don't forget to put them down in our comment section. We want to hear from you. Thank you very much for coming along with us. It's a wrap for today.